The overall goal of this procedure is to synthesize novel catalytic materials with nanogold intercalated in the walls of mesoporous silica. This is accomplished by first forming my cells with the addition of surfactant, which act as a template for the formation of mesoporous silica. A silicon source and a surface modification agent are then added to the solution before adding a gold precursor dropwise to result in nanogold particles. After stirring for 24 hours, the solution is transferred to an oven for hydrothermal processing. During the hydrothermal processing treatment, silica is polymerized to form its mesoporous structure, and gold precursor starts to grow at the nanoscale. The final step is to calcine the material to remove any remaining surfactant and obtain a well-defined mesoporous structure. Ultimately, physisorption, X-ray diffraction, and transmission electron microscopy are used to show that gold nanoparticles are intercalated into the well-defined walls of the mesoporous silica.
The main advantage of this method over others such as direct precipitation is that the materials synthesized here are very thermally robust.
Generally, individuals new to this method will struggle because successful synthesis requires precise control of temperature and solution conditions.
Nanotechnology is defined as a size regime, the nanoscale regime, in which the properties of a material change as a function of changing the size of the particles. In this case, we're talking about gold nanoparticles, and gold also suffers from being a soft metal that's easily melted. So the proof of principle here that we can demonstrate for adding thermal stability to gold should be applicable to all metals.